which will be a case study on the collapse of the Interstate 35W highway bridge, in USA. And this would be my first case study which I'm presenting to you. There will be few more which will be followed up subsequently. So this particular bridge, which is called Interstate 35W bridge, it collapsed on 1st of August 2007 in the evening. That was a peak time when most of the office goers are on the road. And this bridge is located in Minneapolis, a place in Minnesota, USA, which is on the north side. I will tell you the exact location. And this was built in 1967. That means it collapsed after about 40 years. Since it was a peak hours, some 50 odd vehicles actually were there on the bridge and they were drowned. Fortunately, the casualty was only 13 and some 150 people were injured in the collapse. Investigation to this collapse was carried out by, in US, normally the National Transport Safety Board is there, who generally performs the investigation on behalf of the government. And they try to identify the major safety issues and what are the lessons to be learned. And accordingly, they give directions to the federal highway authorities and the state authorities as to what is to be done for future. That is their job. Now, in this particular case, the NTSB, after the forensic structural investigation, did make recommendations to FHWA and AASHTO officials. AASHTO is their, American Association for State Highway. They develop codes like we have in India, IRC codes. Similarly, in US for bridges, we have AASHTO codes. And so therefore, based on the failure, the NTSB has given recommendation as to what changes are to be made in the codes, what changes are to be made in the policy framework so that these are prevented. So this is ideally an ideal situation. This is what should happen in case there is a failure of any structure. This is the broad outline of my presentation. Let me just mention that I was not involved in any manner, neither in the design of this bridge nor in the investigation of collapse. All my presentation material that I'm going to give you is basically taken from the material available in public domain, either in books or in, if you just Google, you will get a lot of material and maybe more than what I am presenting here. So my suggestion and advice to all students, if you want to go further, dig further into this subject, you can freely Google and get a lot of information. So basically most of my case studies would be having this content. That means this will be in 4 parts. First, I will talk about the collapsed bridge, its salient features. Then I will talk about the history of maintenance of the bridge. Then third will be the possible cause of collapse. And the final conclusion by mentioning what are the lessons that we learned from this collapse. This would be a standard content sheet for all the case studies that I'm going to present henceforth. Now let me begin with the first part, which is about the collapsed bridge. Now this I-35W, let me first make it clear that what does it mean. Actually, I-35 is Interstate 35W. W means west. So this is an interstate highway in US, in the state of Minnesota, passing through the downtown of Minneapolis. So all the state highways in US, they will be having the similar kind of terminology. Now, this shows the general arrangement of the bridge, giving the structural arrangement. The bridge was 8-lane. It used to carry 8 lanes of traffic, 4 lane into 2, that is divided carriageway. And it has 14 spans. If you can see pier number, pier 1 to 13, there are 13 piers, and therefore there are 14 spans. And as I mentioned, the bridge was completed or put into service in 1967. It took about 3 years for construction. The construction began in 1964, and it was completed in 1967. And the you know, if you see the span configuration, you have the central long spans, 3 long spans, which is basically there is a stream here, and therefore no pier could be placed in the stream. Therefore, this long span of 139 meter, this is the main truss. And since this long span is 139 meter, the adjacent spans were kept 81 meter. This is basically to balance this particular type of structure, and thereafter it is on land, and therefore the spans are on the less. So in all put together there are 14 spans, but out of which the main portion of the bridge which collapsed is this particular span, that is pier P5, P6, P7, P8. This particular module has failed, and that too particularly between P6 and P7, that triggered the failure. And we will talk in detail. If you see the location of the bridge, you can see this is the location of the bridge. This is the map of United States of America. So this is on the northeastern side, a state which is there, and the bridge is having. If you see the cross section, this is the cross section. There are 2 trusses. If you see the cross section of the bridge, let me explain. There are 2 trusses, one truss here and the other truss here, and the elevation of the truss is like this. And if I cut a cross section, at every node of the truss, there is a transverse truss again, which is basically supporting the deck slab with stringers. So first there is a longitudinal truss, 2 numbers. In the transverse directions, there are truss at every node. Then there is on top of this transverse truss, there are longitudinal stringers, as you can see, more numbers. And on top of that, you have the concrete deck slab. This is the configuration. The main span is 139 meter. The immediate approach spans are 81 meter each, and thereafter the other spans are ranging from 51 meter to about 9 meters. The last span is only about 9-10 meters deck slab. Solid RCC slab. The other spans are all composite deck. Normal. This is a truss type. These are composite deck type, and the last one is RCC slab type. This is a blown up of the location plan. The bridge was located, as I said, in Minneapolis, which is Minnesota's the largest city, and it connects the neighborhoods downtown of East and the Mercy Homes. The south abutment was northeast of the Hubert Humphrey Metrodome, whereas in the north side you have the university. So this is the location. This is a river, Mississippi River. Mississippi River, you may be knowing, is the second longest river in US, only next to the Hudson Bay drainage system, and it is one of the major rivers in US. This shows the now I'm going into the details of the bridge. You can see we are now looking at the main truss, which is 139 meter, 81 meter, 81 meter. Okay. The deck truss, if you can see, these are the main deck truss. Okay. This is one, and this is the second one. This is one plane. This is a view taken along the direction of traffic. On top of this slab, the traffic goes. What you are seeing here is the 2 trusses, which are basically connected each other by bracing. And on top of that, you can see the deck truss, transverse deck truss. Okay. Now let me just give you some idea about the depths. The bridge, the truss depth here at the pier, if you can see, it's a variable depth. Here the depth is about 18.3 meters, and at the midspan it is tapering. At the midspan the depth is 9 meters. And if you see the transverse trusses, they are of 12 feet, means about 3.6 meter. And on top of that, you have the stringers, which are very small. And on top of that, you have a 200 thick deck slab. This is the structure. Now, what you see on the left hand side is a typical connection of the truss members. I don't know whether you people have done any course on trusses, but normally a truss, the members will be connected by means of a plate. If you see this plate, it is called the gusset plate. And the gusset plate connects various members, whether it is a top member or a bottom member or diagonals. The connection is done here. You can see the connection is by rivets. And these rivets are basically joined by a plate which is called the gusset plate. Now, the problem in this particular bridge, the basic reason for collapse was a wrong design and the wrong provision of gusset plate. So, therefore, I am focusing more on gusset plate here. So, this particular view of the truss, this is half truss. You can see this is the 81 meter span part, and this is half of the central span. So, it is, you can consider this, only half is shown because the other half is a repetition of the same. And you can see what is shown in this is in different color the gusset plate and their thicknesses. So you can see that gusset plates provided are of different thickness, and some thicknesses are 1 inch. You see, in US most of the drawings will be in foot-pound system. So though we are familiar with millimeter, meter, MKS, SI system, but there it is all FPS system. So half inch means about 13 millimeter. 1 inch is about 25 millimeter. So you can see the thicknesses are different in different gusset plates, and the red ones are the minimum thickness, which is half inch. You can see the red ones are at L3, U4, U10, L11. They are only half inch thick gusset plates. And let me just mention now that the trigger for the failure of this bridge was the from U10, which is the only about 13 mm thick, where carrying maximum load, and that was one of the trigger for the failure of this bridge. We will talk about it in detail now. So design error in gusset plate is the primary reason. Other reasons for failure was, though this bridge was regularly inspected, but in the inspection records, nobody used to inspect and report the gusset plate. Gusset plate used to be considered till the failure of this bridge. In all the inspection, you see the inspections of a bridge is done in a formatted manner. The inspector has a format, he has to fill the format and put it on record. In that format, there was no provision to inspect the gusset plate and write whether the gusset plate is in order or not. All other components was there, like diagonals, top chord, bottom chord, everything was there in the format. But the format did not have any provision for gusset plate. And this was considered to be, a sort of after this collapse, this was introduced in US. In all subsequent inspection, gusset plate was also supposed to be inspected. Now, this shows the bridge from some other angle. This is the view on your left. You see the bridge in service before collapse, and you can once again see this is about 18.3 meter. At the midspan, the depth is about 9 meter, and you can see the transverse trusses connecting the deck slab, and you can, I don't know whether you are able to see the stringers also. And the one which is on the left is after the collapse. You can see what has happened to the bridge. Many of the vehicles are still stranded on top. This is another pictorial aerial view of the bridge, which is on the next day. It was on 2nd of August. The picture is taken, showing a beautiful picture. What you see, the second bridge, which is adjacent art, beautiful art bridge, is old bridge. It was constructed much earlier, and this bridge is, of course, one of the very famous bridge which is there. This shows some other pictures, a very catastrophic collapse, because as I said, it was in the peak hours, evening, and some 50 vehicles actually got drowned. Uh, so therefore, you can see this holy picture of the collapse a day after the actual collapse. Now, this one is to indicate what is the type of bearings provided. Just let me mention that you see this particular bridge was supported on bearings, and the blow up of the bearing, you can see this picture in the middle, which shows how the bearing is, corroded. This was before the collapse, and you can see just the condition of the bearing. And this picture was taken, of course, long back during service when it was not so corroded. And post collapse, separately this view is taken. Now, the bridge is actually on roller bearings and 3 point at 3 points. At this point number, uh, this is called P5, not written here. You can see in this particular point E, whatever you mention E, what is mentioned as E, are the points where you have roller bearing. That means it allows the structure to move freely to account for the expansion and contraction due to temperature without causing stresses. And that is why you have the roller bearing here. But you have to fix the entire structure at one point. So at P6, this is P6 pier. At P6 pier, it was fixed. So this is a fixed pier. These are free piers. We call them free piers because they are having roller bearings, which are free to move the superstructure without causing any stress. In fact, the reason for corrosion, such an extensive corrosion here, was basically there is an industrial chemical pollution nearby this particular area, and many members got corroded. And of course, during the inspection, it was also noted, and some remedial measures were taken in between. Except for the guzzle plates, they have taken care of the other components. But very interestingly, there was so much of pollution in that area due to the industrial pollution that it was reported after collapse, after investigation, that about 13,600 tons of contaminated soil was removed from below this particular bridge and burned and utilized as a fuel for power plant between 1993 to 1998. This was going on, which means all the benefits of this industrial pollution in terms of recycling of the soil and taking benefit was going on. But nobody realized that this was also causing a lot of problem in this particular bridge. This is another close-up view of, just to show how the bearings are. You can see at this point you had the fixed bearing. At this point you have the roller bearing. You can see the roller so much. And what they realized during the inspections before the collapse many a times, that this rollers due to corrosion got jammed. And this was also one of the attributes for the collapse of this bridge subsequently, because once the roller is jammed due to corrosion, which means it is not allowing free movement or free expansion of the bridge. And if you do not allow free expansion of the bridge, it would mean that there will be additional secondary stresses developing on the structure, and that was not accounted for in the original design. Now, one more thing at this point I would like to mention, that you see this was designed way back, in '67. At that point in time, the technology or the understanding of bridge behavior was not so much developed as today. Nobody at that time talked about fracture critical bridges or bridges. Uh, you see, this is a typical fracture critical bridge. What is meant by fracture critical bridge? If you have a bridge where if a single member is cut from here, that would lead to collapse of this entire bridge. It is called fracture critical. That means you do not have any redundancy in the bridge. So this bridge, normally a bridge which is having only two trusses. So any member of the truss, any of these two truss, any member, if you cut, the entire bridge will fail. So this was a flaw, but this was not a flaw. You cannot consider it to be flaw at the time of design, because at that time, these concepts of fracture critical bridges, this concept of need for redundancy was not really realized at that time. It was only much later in early 70s that people started realizing these are also important. So if you see the modern bridges, if the same bridge is to be done here, nobody will do with this kind of fracture critical bridge concept. So post this particular collapse in US, there was a lot of realization about it. They immediately surveyed all the bridges in US which are long spans and which are fracture critical, and they identified that there are many bridges which are fracture critical, and they had a different inspection roster for those fracture critical bridges. They require more frequent inspection because it is realized that any member failing in that particular fracture critical bridge can lead to the collapse of the bridge, which has happened in this particular case. So therefore, the fracture critical system has been identified after this collapse, and accordingly actions were taken. Now, let me just show you, some snaps in quick succession, which was taken in a security camera at the time of collapse, and you can just see how the collapse has taken place. This is the first, and you can see how the collapse takes place. Okay. So I will just run it all over again, okay, so that you realize. So this is the bridge in fully operational condition. Then you can see, if you see here, there is a kink. You can see there is no kink all along. There is no kink here, but there is a kink here in this zone, which is actually, this is the U10 gusset plate. Okay. You can see there is a kink here. The trigger for the failure is here. You can see. And at this point, you can also see there is a lot of material on top of the deck. And I will tell you subsequently, these are also main reasons for collapse. There are a lot of construction material which was dumped on the deck, on top of deck, and which caused the collapse. So you can see the dust. There are two type of dust. One dust is when the structure is falling on the ground and the dust created from the structure which is falling on the ground. Another level of dust is being created from top of the deck, which is because there is a lot of aggregate and sand which was piled up on top of the deck, and that is also creating a dust. So I have a small video to show an animation. It's a very small video. I would like to show that. I would like to move forward. I think. Yeah. So I think we now go to the next part of my presentation, which is history of maintenance of the bridge. The bridge has, in fact, had a long history of maintenance and repair before it actually collapsed. Am I audible now?
Yes, sir. Yes, sir.
Okay, okay, okay. Okay. The way back in 1990, this bridge collapsed in 2007, but way back in 1990, 17 years before the collapse, the bridge was classified as structurally deficient by the US Department of Transportation because corrosion of the bearings prevented sufficient movement, as I mentioned earlier. And the classification was based on a score of 4 or lower on a 9-point rating system. So it was, now what is structurally deficient? Let me clarify here. The level structurally deficient doesn't mean that the bridge is unsafe. It means that the bridge would require significant maintenance and repair to remain in service, but it is not unsafe still. So, but it is a red flag. Then in 1993, the federal transportation officials increased the frequency of inspection of the bridge from once every 2 years to every year. Because of this red flagging, they had to change the roster, and they used to inspect every year. And they find some corrosion of steel in the bridge joints and fatigue cracks in the bridge approach spans. So therefore, they took care of this. 1999, the bridge was fitted with a de-icing system. You see, the bridge is actually located at a place where the climate is very, very cold, where the snowfall was very rampant, and therefore they have to have a de-icing system installed in the bridge deck and railings. And eventually, let me tell you, they have increased the dead load by all these means by more than 20% in this particular bridge. And that is also one more reason for the collapse. In 2001, there was an independent study by University of Minnesota, and which once again deems the bridge as structurally deficient. But at that time also they mentioned that although it is structurally deficient, but it doesn't require immediate replacement. Then in 2004, 2007, another independent study was carried out by URS Corps exploring the bridge's fatigue potential. You see, by that time, the understanding on fatigue of steel structures was quite developed. Not at the time of its original construction and design, but at the time 2000, 2004, 2007, a lot of fatigue problems were there in fact, all the bridges in US, steel bridges. and here also there was no exception. Additional steel was recommended, additional steel plates to critical members to reinforce the trusses, and to re-inspect the welds in the trusses to monitor the bridge's usability. Uh, then transportation officials chose to re-inspect the wells and begin the work from May 2007. And they found that whatever measures were taken earlier, no growth, further growth in the existing well cracks was there. So they were quite happy that the crack is not further developing. In summer 2007, that is just um, uh, month before the collapse, 2.4 million was spent in repair and maintenance, which was being conducted on the bridge deck. In fact, the lot of construction material I was talking about on top of the deck was mainly a part of the repair work which was going on at the time the bridge collapsed. A study of the inspection reports prepared by Minnesota Department and the owner, as I mentioned, it indicated that the bearings were jammed and loads were increased by 20%. All this was realized before the collapse. And you can see, if you can see here, what is the level of corrosion on the bridge, which was seen at that time. Uh, Now, how this load developed, also there is a history, and this particular slide covers that. In 1977, the state increased the bridge deck thickness about by 2 inches. This renovation increased the dead load by 13.4%. In 1998, the state increased the dead load by another 6% when it installed the median barrier, which was not there earlier. Together, these two renovations increased the weight by about 20%. And then third set of renovation to resurface the bridge began in June 2007, 2 months before the collapse, when these construction materials were there on top, and they were overlaying on top of that, adding few more percentage of dead load. This is the view of a typical, very close-up view of the bearing. You can see the level of corrosion here. Uh, though in the NTSB investigation, they did not point out this to be the cause of failure. They said that although the bearing was in bad shape, although it was corroded, but this was not the cause of collapse. That's what they mentioned. Now let's focus a little bit on the gusset plate. You see, during the routine inspection, those who were inspecting at regular interval, they used to take photographs, and they have also noted that the gusset, you can see the gusset plate here is buckled already, and this was when the bridge was in service. All these were noted. The inspectors also noted that they are buckling, but they did not report it because the inspection roster. Can you please mute? I request all to kindly mute so that presentation can be continued. So this buckling was noted earlier, and you can see how these gusset plates after failure they were placed, and you can see how the location. This is the U10 I mentioned. What is the situation there? You can see it is badly has badly failed. So, according to a 1998 inspection report, there are numerous fatigue cracks found in the approach spans. These cracks were located in the negative moment regions where the diaphragm web stiffener was not welded to the top flange. And the bridge was designed and constructed in 1970 when there was very limited understanding of the fatigue behavior of welded members and connections. Now I will come to the possible cause of collapse. So far we have seen what the bridge general arrangement is and what is the history of maintenance. Let me now focus on the possible cause of collapse. Well, before we go into the possible cause of collapse, let us understand the climate of the area. Minnesota has a humid continental climate with hot summers and cold winters. there are occasional snowstorms, there are floods, there are tornadoes, and there are uh, fire hazards, which are very annual feature. And I mentioned that the trigger for the failure was the gusset plate failure at U10 joint. However, it will be too sort of simplification, too much of a simplification if I say that is the cause of failure, because there is an overloading, there is a lack of inspection of the gusset plate, and also during the failure, at the time of failure, there were construction loads on top, which was far more than the design life load. So all these caused the failure. Maybe the trigger was the wrong design of the gusset plate. So this is the trigger of the failure, as I told you. U10 actually it started from here, though U10 or U10 dash is symmetrically placed, but it started from here, and I will tell you the little more detail. You can see this is the point where it really failed. So possible cause of collapse: design error, inadequate load capacity of the gusset plate, thickness provided was half that is required, design was deficient even as per the prevalent codes and practices at the time of design. Inadequacy in design review process, no proof checking was done at that time, neither federal nor state authorities evaluated the design, and the process of proof checking was not done, it was not a standard practice. No importance given to the gusset plate in the design and in the load rating. And I mentioned about the dead load increase in various times. Original design, the load was here. Then the load increased in 1977 modification. In 1998, further increase in 2007, further increase before it actually failed here. So you can see this is a good way to demonstrate how the load has increased over the years. Then added construction debris or construction load on top of the deck at the time of failure is another reason. Forensic analysis result by NTSB. The analysis points out these 5 points: insufficient bridge design firm quality control procedure for designing the bridge, lack of guidance for bridge owners with regard to the placement of construction load on bridges. Whenever you do construction, you have to take permission from the authorities as to how much of load you can place on an existing structure. And this has been ignored. In fact, this is ignored in many cases. Even I'm sure in India also, when the contractor works, very little guidance is there as to what do's and don'ts. Then exclusion of gusset plate in bridge load rating, lack of inspection guidance for condition of gusset plate distortion, inadequate use of technologies for accurately assessing the condition of gusset plate. Another, you see, whenever there is a failure in any structure, it is not one agency who is actually doing the investigation. One agency is appointed by the authority, the client, to investigate. And in this case, it is NTSB who was engaged by the owner. But you see, other parties, the affected parties or the victim or the contractor also appoints parallelly a investigating agency, because every agency will have to safeguard their interest after the collapse. Otherwise, they will have to pay a heavy penalty, because the forensic investigating agency will always look at the bridge failure from the perspective of their client. If it is an owner, it will be from owner's perspective. If it is a contractor, it will be from contractor's perspective. And in this case, even the victims, those people who actually were killed in this collapse, they appointed another agency, which is Thornton Tomasetti, a very famous consultant, and they did a parallel investigation, forensic investigation, and they came out, though in general they agreed broadly with NTSB, but they had a different perspective on the failure, the trigger for failure. They have a different perspective on the trigger. So studies by this team of from Thomas Etty, it included the assessing the impact of the fatigue, temperature, load distribution, etc. And they did a forensic information modeling, very interesting interactive computer graphics, and their findings pointed to failure of bearings as a trigger, which caused the failure, not the gusset plate as a trigger. Though they also recognized that the gusset plate also was under design. Although all the other things are fine, but they, according to them, the trigger for the failure was the jamming of the roller bearing. So they carried out a very detailed investigation. They carried out a local analysis of the non-linear local analysis of the gusset plate, bottom cord. They carried out a global analysis of the collapse situation, and they used this, forensic investigating modeling, a very, something which we do not do in India so far. And then based on that, they came out with, you see, this is their model in FIM, and you can see this is the portion which is that U10. This is the portion which actually failed, but it failed according to them due to the jamming of the bearing here. And this is a photograph to show the various members placed, that U10 thing placed from the parts components picked up from the collapse, and they put it on the ground just to replicate the two truss, one side of the truss, the other side of the truss, and this is just to make people understand as to how the what is the status after failure. Very nice way of sort of analyzing, investigating a collapse. So what according to them is happened is that due to this jamming, there is a tension, additional tension due to that which occurred in lower member L11, L9, a compression, not tension, sorry. And due to this compression, this member buckled. You can see this member buckled. And due to this buckling, there was additional force on already weak gusset plate at U10. And finally the gusset plate here, you can see it just failed, it just teared off here. And many photographs I shown you earlier demonstrated this. So I think I will now show another small video, very interesting, which tells you in a very great detail this particular failure. And I think
Sir, we can't hear anything. The audio is not there. Is it?
Well, I think okay. So am I audible now?
Yes, sir. Yes, we can hear.
Could you listen to the audio in this video, or audio was not there?
No, sir, we can't hear anything in that video.
Oh, I see. Uh, I will do one thing. In that case, I will also send the link,
Okay.
which you can share with others so that they can see it.
Okay, sir.
Because I was able to listen from here, but maybe if it is no problem, I will send the link
Okay.
directly
Yes, sir. I
so
will
that
share in
it
the
can be
group.
shared with the yeah. What about the previous one? The previous video which I had shown?
Yes, sir, that audio we can hear in that, sir. Previous one.
There, acha, you could hear the audio there, but not here.
We're not here.
I see. Okay. So I come to the last part of my presentation, which is on the lessons learned from the collapse. And what briefly I will tell you, for all existing fracture critical truss bridges, I have defined what is fracture critical truss bridges, that is non-load path redundant steel truss bridges. The bridge owners shall have increased frequency of inspection. Load capacity calculations shall be conducted for those bridges to verify that the stress levels in all structural elements, including gusset plates, are within applicable requirements. This is the lesson that we learned from this collapse. And I think we should apply this even in bridges in India. When you now go out and look at the bridges, you first try to see whether the bridge is fracture critical bridge or not. And if it is a fracture critical bridge, you have to have in your mind that this is a bridge which requires more inspection as compared to other bridges, and you need to make sure that each and every component of that bridge is working so that the bridge do not collapse. Second, for new bridges, there is a need to carry out thorough proof checking of design by the bridge owners to detect and correct any bridge design errors before the design plans are made final. So independent checking of the designs before execution is a must, because every human being can commit errors. Designers, no engineer is infallible. We can also commit error. The process should ensure that there is no error which is transmitted. If I have committed one error, my proof checker should be able to detect that, and therefore a screening is extremely important. Gusset plate is an important structural element. Design of this component deserves some attention, same attention as any other component of the bridge. Inspection of truss bridges must include condition assessment of gusset plate as well, which was not there in this particular case. Develop specifications and guidelines for use by bridge owners to ensure that the construction loads and stockpiled raw materials placed on structure during construction or maintenance do not overload the structural members or their connection. That is also another lesson that we have learned. So with this, I close my presentation. Thank you very much for your patience. Thank you. I can